All right, so we're in section 5.4 here. We're getting very close to the end. One more section to cover after this. And we're talking about indefinite integrals and the net change theorem. So far we've introduced the concept of a definite integral, and the motivating concept behind that was finding the area under a curve. And then in the previous section, 5.3, we developed a really useful technique, the most important theorem in all of calculus, called the fundamental theorem of calculus, which is used to evaluate definite integrals. And here is the statement of that theorem. If big F is an antiderivative of little f on some interval a, b, then the definite integral from a to b of f of x dx is equal to big F of b minus big F of a. So because we're dealing a lot in antiderivatives, it's going to be helpful to have a specific notation for the antiderivative of a function, as opposed to just saying find the antiderivative of f every single time we need to do that. And the notation that we're going to use is the integral symbol, but without a lower or upper limit of integration. So if we see something like this integral symbol of f of x dx, what this means is the most general antiderivative of little f of x. And again, remember, if big F of x is any antiderivative of little f, then big F of x plus c, where c is some arbitrary constant, represents the most general antiderivative of that little f. We're going to refer to this thing here as an indefinite integral. So now we have definite integrals, which have limits of integration, and we have indefinite integrals, which do not. Definite integrals, like this one, are equal to a real number, right? When you work this out, it comes out to some number, like 3/2 or -6 or pi or something like that. Indefinite integrals come out to functions, not real numbers, because the result is an antiderivative, which is a function in its own right, okay? So here for reference, we have a table of indefinite integrals, and this is just the same table. This is the same table of antiderivatives that we have seen already. So what we're going to be doing is, I'm not going to go through all of these because we've already seen these before, and these are just the derivatives that we've evaluated, but in reverse. We're going to start evaluating a few indefinite integrals just for practice. And really, there's no difference between what we're doing here and what we did back in section 4.9 every time we were asked to find the most general antiderivative. So instead, what I'm going to do is just use this notation as we're evaluating. So here we want the indefinite integral of 5x cubed minus 4 over x plus 2 secant of x tangent of x. And again, we're thinking in terms of antiderivatives. So what is this equal to? Well, I would add 1 to the exponent here and then divide by 4, which would give me 5/4 x to the 4th. That takes care of this first term. Minus 4 over x. This is the same thing as 4 times 1 over x. And the antiderivative of 1 over x we know is the natural log function. We're seeing that one right here. But we put an absolute value over the x when we do that. You have to remember that. So the 4 there becomes a coefficient. 4 times the natural log of the absolute value of x. Finally, secant tangent of x. We recognize that as the derivative of the secant function. So this becomes plus 2 secant of x. And then I have to include that plus c. Every calculus teacher who has ever taught Calculus 1 will tell you that students very frequently forget to put the plus c here when they're doing this indefinite integral. And it becomes a pet peeve for a lot of calculus instructors. And so we will generally dock you at least 1 point on a problem showing up on an exam where you're supposed to evaluate one of these. Do not forget that plus c if this is an indefinite integral. All right, now let's evaluate this next one, the integral of 2t minus 3 times t plus 10. So this is a product of two things, and we don't yet have a counterpart to the product rule for integrals or antiderivatives. You will right at the beginning of Calculus 2. You introduce something called integration by parts, which is the counterpart of the product rule when you're doing antiderivatives. We don't actually need that though, because this can be evaluated simply by multiplying this out. If I multiply these two binomials out, 2t squared plus, this would be plus 20t minus 3t, so that's plus 17t minus 30 dt. Now, what do I do here? I use the power rule in reverse. Add 1 to the exponent, which is 3, and then divide by 3. 2/3 t cubed. Here, add 1 to the exponent, so t squared, and I divide by 2 there, plus 17 over 2 t squared. And then we know constants, like this one, 30, we'll just get a t there. Notice that I'm not using x's, I'm using t's, so be careful about the variable that you're using, and don't forget to write plus c. Okay, let's do some more. I'd like to evaluate the indefinite integral of tangent squared of u du. And what we're going to be doing here is noting that the tangent squared function does not show up in this table of indefinite integrals anywhere, because the tangent squared function is not the derivative of anything that comes to mind immediately. So as is often the case when you have trigonometry in an integral, if you don't know what the antiderivative is right away, you might need to do some simplifying using trigonometric identities. Now the tangent squared function from trig I know is the same thing as this. Secant squared of u minus 1. This is a version of the Pythagorean identity. Ignore that little mark right there. So using this identity, the secant squared function is a familiar derivative. Its antiderivative, or an antiderivative for that, would be the tangent function, tangent of u, right? The derivative of tangent is secant squared. And then this minus 1 here becomes minus u, and I get that plus c at the end. That's called the constant of integration. Okay? Not too bad. So you notice these problems are going relatively quickly, and it's just because I'm familiar with my antiderivatives. So I'm pretty easily coming up with these antiderivatives just with very little work needed. We're going to see, starting in the next section, that most integrals are not this easy to evaluate. So we're just kind of starting off with the simplest cases here. All right, next up, I'm going to evaluate the square of 1 plus r over r, okay, dr. And for this one, just like 2 problems ago, I don't want to try and deal with this directly. Instead, I want to multiply it out, okay? Because, again, you can't apply the power rule directly here. You can't apply the quotient rule because that's for derivatives, not antiderivatives. We need to simplify this first. So this is equal to, if I square the numerator, 1 plus 2r plus r squared over r squared. I squared my numerator and denominator, dr. And as we've seen in previous examples, you want to keep simplifying this. Divide everything by r squared. So I'm going to get r to the negative second power plus the r and the r squared cancel. That becomes 2 over r, or 2r to the negative 1 power. R squared over r squared is just 1. Okay, now I can use my power rule in reverse. So once again, add 1 to this exponent, which is going to give me a negative 1, and then divide by that amount, which gives me negative r to the negative first power. R to the negative 1 power is the same thing as 1 over r, and as we've seen, the antiderivative there is the natural log of the absolute value of r. But I have a plus 2 here, so that 2 becomes a coefficient again. Okay, and then this 1 we know will become just r. And then plus c. Have to include that plus c. Okay, so that's all good. And we could do lots and lots more examples, but because we've done so much with antiderivatives already in section 4.9, and then even in the previous section where we used them to evaluate definite integrals, it's kind of just more of the same. So there's not much point in doing more examples. Now we're getting into the main subject of this section, something that we call the net change theorem. So the fundamental theorem of calculus, part 2, I can restate it by putting the capital F in here, capital F prime of f of x. If that's my integrand, then big F would be the antiderivative of f prime, right? So another way of saying the fundamental theorem of calculus is that if capital F of x is continuous on the interval AB, then the definite integral of AB, if capital F is more than just continuous, if it's differentiable, so f prime of x if I'm integrating that from a to b, it's equal to big F of b minus big F of a. Now, the reason I'm putting it in this form is because I'm establishing a more obvious connection between this integrand and these numbers here. And focusing on the right-hand side of this equation, F of b minus F of a represents the net change in our function f corresponding to the change in x from x equals a to x equals b. If you think about difference quotients, when we talked about difference quotients, a difference quotient, we define that to be f of x minus f of a over x minus a. In the numerator, f of x minus f of a corresponds to the change in f from a to x. And then the denominator represents the change in x itself. But the numerator, notice it kind of resembles this. Specifically, that is a difference of the function evaluated at two different values. We already have used that difference to represent a net change. And so that's what this f of b minus f of a represents. It's a net change in our function f as x goes from a to b. But that exact difference right there could be alternatively written this way according to the second part of the fundamental theorem of calculus. So what this is saying is that if we want to find the net change in a function f as x goes from a to b, and we happen to know the derivative, which represents the rate of change in that function, then integrating that rate of change from a to b gives us that net change. That's what this is saying. Okay? Now there's all sorts of examples. Your book goes through and lists a whole bunch of different examples of rate functions that represent a rate of change, which are integrated, and what the corresponding net change represents in applications. I'm not going to go through that whole list because we're going to use examples to illustrate this where we work through them. But I want to point out that we've already done this before. We've already used this application. So again, remember, we have this relationship that we've talked about since as far back as when we first introduced derivatives, the relationship between the position of a moving particle at time t and its velocity. We know that the velocity function is the derivative of this position function. Now specifically, if I wanted to determine the net displacement of a particle, meaning what was its change in position from time A to time B, that change, as we kind of talked about up here, would be S of B minus S of A. That's its change in position, right? Which looks like the right-hand side of the net change theorem, where capital F is just S. But if this F here is represented by S here, then this F prime in here should be the same thing as S prime. But S prime is the same thing as the velocity function. And so what this is telling me is that if I want to know what the net displacement of my particle is from time A to time B, then what I need to do is integrate my velocity function from A to B, and it gives me that net displacement. This is also kind of the same concept that we looked at when we introduced the definite integral, and we're looking at its relationship to the velocity and position functions. This is making that the work we did there basically complete. It's establishing that we were on the right track back then. So in the next video, we're gonna look at an example using this idea.